Now, this is quite a story from NASA because for the second time in history, a man-made object has left our solar system.
NASA making a historic announcement today that the Voyager probe has entered interstellar space, that place between the stars. It's now out beyond the sun's heliosphere.
Voyager 1, humanity's most distant spacecraft, has once again stunned scientists with an extraordinary discovery at the outermost boundaries of our solar system. Decades after its launch in 1977, and long after it passed beyond the planets, Voyager 1 continues to defy expectations. Now traveling through a region known as the helipause, the outer edge of the heliosphere where the sun's influence gives way to interstellar space, the spacecraft has detected a signal and phenomenon that experts had not predicted nor fully understood. This recent finding has not only ignited new debates within astrophysical communities, but also revealed fundamental questions about the nature of space itself. Before we start, smash the like and subscribe buttons for more updates. The region Voyager 1 currently occupies is not just a borderland. It's a transition zone between the solar system and the interstellar medium. Previously, scientists assumed that this area would be quiet, perhaps even empty, a kind of cosmic no-man's land where particles from the sun thin out and the effect of the galaxy begin to take precedence. However, Voyager 1 sensors have recorded something unexpected. A persistent low-frequency humming, a constant drone of plasma waves unlike anything measured before in this location. The signal does not fluctuate with solar activity, meaning it appears to be detached from the rhythm of the sun, a surprising contradiction to previous assumptions that solar events dominate the behavior of particles even at such great distances. This continuous plasma wave, detected by Voyager 1's plasma wave subsystem, has offered a new insight into properties of the interstellar medium. Rather than being a passive environment, interstellar space now appears to be alive with faint vibrations, invisible to the eye but measurable through the right instruments. The implication is profound. The space beyond our solar system is not silent, but rather a subtly dynamic environment filled with energy and motion. The vibrations are believed to be caused by the extremely diffuse gas and dust that exist in this region, oscillating under the influence of galactic forces. What makes this discovery even more remarkable is that Voyager 1's instruments were never specifically designed to detect such phenomena, yet they continue to function well beyond their expected operational lifespans. This phenomenon challenges existing models of the interstellar boundary. Traditionally, scientists imagine a helipause as a clear-cut barrier, a bubble-shaped limit pushed outward by the solar wind. It was thought to act almost like a membrane, separating our sun's domain from the chaotic void beyond. But the data from Voyager 1 now suggests that this boundary is far more permeable and active than previously thought. There appears to be a kind of interaction zone where solar and interstellar forces mingle, merge, and perhaps even compete. The discovery of the plasma wave hum provides evidence that particles and fields may interpenetrate this boundary more significantly than anticipated. The consistency of the signal is equally baffling. Most cosmic events are sporadic or cyclical. Solar flares rise and fall. Interstellar radiation varies with cosmic rays, and even magnetic fields pulse in erratic patterns. Yet this hum has persisted steadily for years. It suggests an underlying structure or mechanism in the interstellar medium that is yet to be identified. It could hint at a kind of cosmic background activity, similar in philosophical importance to the cosmic microwave background, though vastly different in frequency and origin. If proven to be a universal feature of interstellar space, this plasma hum might one day be used to map or identify large-scale structures far beyond our solar system. There's also the question of why this was never detected before. Part of the answer lies in the uniqueness of Voyager 1. No other human-made object has reached this specific location, let alone continue to operate with functioning instruments. Ground-based telescopes, no matter how powerful, cannot measure such faint low-frequency plasma waves across such distances. Voyager 1 has essentially become a deep space ear, picking up the whispers of the cosmos from a vantage point no other probe has achieved. It's a solitary sentinel hearing things that cannot yet be confirmed by any other means, and in doing so, it has introduced a mystery into space science. Voyager 1's detection also raises fresh questions about what lies beyond. If the interstellar medium is not inert, but resonates with such activity, what other phenomena might be present? There could be regions of greater complexity, perhaps denser pockets of plasma, magnetic fields that twist in unexpected patterns, or even interactions from cosmic forces we've yet to classify. The data from Voyager 1 indicates that our understanding of the galactic environment is still in its infancy. For decades, space beyond the helipause was assumed to be a predictable extension of what came before it. Colder, emptier, and quieter. Instead, it may be vastly more diverse, layered, and active. The implications for future missions are significant. If interstellar space contains these low-level plasma oscillations, then spacecraft designed to explore beyond the solar system will need to be equipped to detect and interpret them. This could fundamentally alter the design and objectives of interstellar probes. Rather than simply trying to reach other stars, future missions might take on the task of mapping the plasma landscape between them, treating interstellar space not as void, but as terrain. The environment is proven to be more like an ocean than a vacuum, one with currents, eddies, and pulses that spacecraft must navigate and study. This discovery also lends weight to the idea that space exploration is not only about reaching distant worlds, but about comprehending the vastness in between. The journey between stars might be as rich in science and wonder as the destinations themselves. It reframes the scale of exploration not as a jump from one island to another, but as a continuous voyage through an unknown and resonant medium. The hum heard by Voyager. The first may turn out to be just one voice in a cosmic choir, each tone telling a different story about the history and dynamics of our galaxy. Furthermore, the presence of this plasma hum forces a reevaluation of the heliosphere itself. Long believed to be a relatively stable bubble created by the solar wind, the heliosphere may now be viewed as a more porous and reactive structure. If energy and particles from interstellar space can penetrate this far in, or if solar material can leak outward in subtle ways, then the boundary between our solar system and the galaxy is more interactive than previously believed. This could influence how we understand cosmic ray modulation, solar system shielding, and even the origins of certain high-energy particles observed near Earth. The data also prompt a rethinking of how magnetic fields behave at these boundaries. The interactions between the sun's magnetic field and the interstellar magnetic field are not fully understood, and this newly detected plasma wave activity might offer clues. These waves could be a product of magnetic reconnection events, where lines of magnetic force snap and reconnect, releasing energy. Such events are known to occur in Earth's magnetosphere and on the sun's surface, but they may also be present at a galactic scale. If so, Voyager 1 is not merely an observer of interstellar space, but a witness to cosmic scale processes unfolding at the solar frontier. At the heart of this discovery is a sense of the unexpected. The mission planners who launched Voyager 1 could not have foreseen that, over 4 decades later, their spacecraft would be uncovering phenomena that challenge the boundaries of astrophysics. The instruments aboard were never meant to last this long, nor were they designed with interstellar plasma detection as a priority. Yet through resilience and scientific curiosity, Voyager 1 has become a key to a door no one knew existed. That it continues to function at such vast distances is a technological triumph, and that it continues to teach us is a testament to the layered complexity of space. In a universe often portrayed as silent and still, Voyager 1 has revealed an active soundscape, a plasma resonance echoing across incomprehensible distances. This discovery underscores how little we truly know about our place in the galaxy. It reminds us that beyond the gravitational pull of our star, the cosmos is not an empty wilderness, but a region, humming with life in its own enigmatic way. And while the data from Voyager 1 is sparse, mere drips from a cosmic ocean, it is rich enough to reshape paradigms. Every signal received is not just a technical marvel, but an invitation to ask deeper, more challenging questions. What began as a mission to explore the outer planets has become a journey into the unknown, peeling back layers of the galaxy one at a time. Voyager 1's new detection has stirred imaginations and disrupted theories, reminding us that even after decades of exploration, the frontier remains wild and full of secrets. The spacecraft, now over 15 billion miles from Earth, is far beyond any other probe and continues to relay insights that hint at an even more astonishing universe than previously imagined. This milestone discovery might lead to new branches of astrophysics, ones focused not only on planetary systems and stars, but on the connective tissue of the galaxy. the interstellar plasma that binds and weaves through the cosmos. Scientists will now pore over this data, build new models, revise textbooks, and develop missions with instruments finely tuned to hear what Voyager 1 has heard. It's a reminder that the unknown is not just a place we haven't visited. It's a layer of reality we have only begun to perceive. Voyager 1 has pulled back that curtain just a little, and what it has revealed is both beautiful and bewildering. The universe speaks in many voices: light, gravity, motion, and now, thanks to Voyager 1, we know that it also whispers in plasma. The edge of the solar system is not an ending, but a liminal space full of its own mysteries. Voyager 1, still racing through the dark, continues to listen, and through it, so do we. As Voyager 1 continues its journey into the uncharted expanses beyond the heliopause, its latest discovery of the low-frequency plasma hum is only the beginning of what this distant frontier might unveil. The deeper the probe moves into interstellar space, the more it becomes clear that we're only scratching the surface of a vast and complex domain where each observation has a potential to disrupt long-standing scientific paradigms. Voyager 1 now occupies a position where the environment transitions from protective bubble of the sun's influence to the raw, unfiltered conditions of the galaxy. One of the key unknowns in this region is the behavior of cosmic radiation. For years, it was assumed that the heliosphere shielded our solar system from the brunt of high-energy particles, essentially acting as a buffer against a galactic background. However, now that Voyager 1 is operating beyond this barrier, it is exposed directly to the interstellar radiation environment. It is registering fluctuations in intensities that are helping scientists understand how radiation behaves when no longer moderated by the sun's magnetic field. This data offers insights not just about astrophysics, but also the long-term viability of interstellar travel. Any future mission aiming to send crewed spacecraft beyond the solar system will need to understand the radiation dynamics in this region. How dangerous is it? What kind of shielding would be required to protect both instruments and humans from prolonged exposure? Voyager 1's measurements are providing the first, albeit limited, clues. The radiation intensity beyond the heliopause appears both higher and more unpredictable than many models had anticipated. These findings will inform the engineering of future probes, particularly those that aim to operate autonomously in such extreme conditions for extended periods. An even more profound implication lies in what this region reveals about the structure of the galaxy itself. Voyager 1 is not just mapping environmental conditions, it is offering a tactile sense of our place in the Milky Way. For the first time, humanity is able to receive direct physical measurements from a region influenced more by the galaxy's forces than by the sun. This includes a galactic magnetic field, interstellar particle density, and the complex interactions of interstellar winds. The spacecraft data suggests that these elements are not uniform but vary subtly, indicating a richness and diversity in the galactic environment. Such complexity invites new questions about the nature of the interstellar medium. Is it a smooth, homogeneous field, or does it contain invisible structures, perhaps filaments or bubbles, shaped by past supernovae, stellar winds, or galactic tidal forces? Voyager 1 is beginning to resolve these mysteries by providing empirical data that can be cross-checked with simulations and theoretical models. For example, fluctuations in plasma density and magnetic field strength hint at the existence of boundaries within the interstellar medium itself, zones where different interstellar weather systems might interact or collide. These are not boundaries in the traditional sense, but gradients and contours in the galactic fabric. Another critical facet of Voyager 1's ongoing mission is its ability to detect variations in particle populations over time. Interstellar space is not static, and the spacecraft's instruments have shown that the environment fluctuates in a way that might correlate with galactic scale processes. Perhaps it is responding to the broader rhythm of the Milky Way's rotation or the passage of shock waves from distant cataclysms. These correlations, while tentative, point toward a dynamic and reactive medium that is constantly evolving on both small and large scales. The existence of such variations opens a tantalizing possibility that Voyager 1 could eventually pass through regions of interstellar space vastly different from the one it currently inhabits. For example, it may enter a denser cloud of gas and dust, which could affect the readings on everything from particle density to magnetic field strength. These clouds, remnants of ancient stars and nursery for new ones, populate the galaxy like islands in an ocean. Passing through one would offer a priceless opportunity to study its properties firsthand, an event that has never occurred in the history of space exploration. One of the more speculative but fascinating implications of this journey is its potential to test ideas about dark matter. While Voyager 1 was not built to detect dark matter directly, it travels through regions where gravitational influences might manifest in subtle ways. If the spacecraft were to detect anomalies in its trajectory, deviations not explained by known gravitational forces, it might hint at unseen mass in the surrounding space. This would not be evidence in classical sense, but it could contribute data to a growing body of work aimed at mapping the unseen architecture of the galaxy. There is also a philosophical dimension to this odyssey. Voyager 1 is not simply extending humanity's reach into space. It is redefining the meaning of distance and connectivity. Even now, over 20 billion kilometers away, the spacecraft sends back data that takes more than 22 hours to reach Earth. Yet, this stream of information, delayed as it is, keeps humanity connected to the edge of its cosmic domain. Each bit of data is a physical link between the cradle of civilization and the great unknown. It's as if Voyager 1 is unraveling a cosmic thread that stretches back to Earth, guiding us deeper into a realm that no other living being has touched. As it presses onward, the spacecraft also challenges the notion of frontiers. The edge of the solar system was once imagined as a definitive line, a border between us and them, between the solar neighborhood and the great beyond. Yet, Voyager 1's findings complicate that idea. The heliopause is less a wall and more transition, fluid, leaky, and alive with interaction. The discovery of the plasma hum shows that even the most remote boundaries are not absolute. Instead, they are places of transformation where new forces emerge and old assumptions dissolve. There is also an element of serendipity in Voyager 1's achievements. The fact that a spacecraft launched in the late 1970s, powered by technology considered primitive by today's standards, continues to make groundbreaking discoveries speaks volumes about the ingenuity behind its design and the foresight of its creators. But beyond engineering, it also illustrates the unpredictable nature of exploration. No one could have planned for this mission to detect plasma waves beyond the heliosphere. Yet, the decision to include certain instruments meant originally for planetary studies has now paid off in unimaginable ways. This raises important considerations for future mission planning. Should future deep space probes be designed with broader scientific objectives in mind, even at the expense of mission-specific instruments? Voyager 1 shows that flexibility and durability can lead to discoveries far beyond initial mission scopes. Perhaps the key to unlocking the secrets of space is not always precision, but endurance and openness to the unknown. Another critical aspect of Voyager 1's journey is how it redefines communication in space exploration. The spacecraft signal is incredibly faint, requiring large, sensitive radio telescopes on Earth to detect and interpret it. Maintaining this line of communication over such immense distances is a technological marvel. It underscores the need for advanced deep space communication infrastructure as humanity looks toward more ambitious missions, perhaps to the Oort cloud or even neighboring stars. The ongoing success of Voyager 1 has spurred discussions about laser-based communication systems or interstellar beacons that could sustain data exchange across even greater expanses. Voyager 1 also raises a question of observational perspective. Earth-based telescopes provide data filtered through layers of atmospheric distortion and limited by our planetary vantage point. Space telescopes like Hubble or the James Webb operate in clearer conditions, but are still anchored to the sun's gravitational field. Voyager 1, by contrast, is free-floating in interstellar space. Its observations come from a point so remote and unobstructed that they offer a uniquely pristine view of cosmic phenomena. As it drifts farther, its perspective could help triangulate positions of cosmic sources or refine our understanding of galactic structures based on how interstellar signals shift over distance. The probe may also detect subtle gravitational or electromagnetic effects from objects not directly visible, such as rogue planets, brown dwarfs, or even undetected stars. Its sensors, though limited, could record shifts in velocity or direction caused by the influence of massive objects nearby. While such detections would be indirect, they will provide crucial data for mapping the hidden constituents of our galaxy. Voyager 1's voyage is more than an adventure. It is a slow unfolding dialogue with the universe. With each transmission, it asks new questions. What is the true nature of the space between stars? How does matter behave when no longer confined by a star's magnetic reach? What unseen forces shape the plasma and particles drifting through the void? The scientific community now looks at interstellar space not as a simple environment to traverse, but as a vast ecosystem with its own rules, rhythms, and surprises. Voyager 1 has forced a recalibration of this view. Its instruments are not just detectors. They are translators of an alien language, a language of hums, pulses, and fluxes that science is only beginning to interpret. As the spacecraft continues, it may enter regions of greater interstellar density, possibly even interacting with the leading edge of a distant interstellar cloud. Such a transition would represent a dramatic shift in its environment, allowing scientists to observe for the first time how a spacecraft behaves when immersed in a region shaped not by the sun or its remnants, but by the galactic tide itself. These next stages could be even more revelatory. If Voyager 1 encounters new fields or energies, it might help trace the evolutionary path of the interstellar medium over cosmic timescales. The data could inform theories about star formation, galactic feedback loops, and the fate of matter ejected by supernovae. By tracing how these elements disperse and coalesce, scientists could better understand how galaxies like ours evolve. The spacecraft is also beginning to offer clues about the long-term stability of interstellar conditions. How consistent is the plasma density? Do magnetic fields remain stable over time, or do they fluctuate with invisible turbulence? Are the high-energy particles evenly distributed or concentrated in filaments? Voyager 1 is now positioned to observe changes not just in space but in time, revealing how interstellar space evolves over decades. It may be another decade before Voyager 1's power systems finally fail. Until then, every byte of data it sends home is precious. The insights gathered in these final years may form a foundation for a new era of space science, one that prioritizes not just destinations like planets and moons, but the space between them, where much of the universe's mass and energy may actually reside. Voyager 1 is not just a spacecraft. It is a statement, a testament to what humanity can accomplish when curiosity is allowed to stretch its wings. It represents the best of scientific inquiry, resilient, patient, and ever-reaching outward. The recent discovery of the interstellar plasma hum is just one song in a larger symphony that Voyager 1 is revealing, the hidden music of the cosmos. And as this lone traveler continues to pierce the darkness, it becomes increasingly clear that space is not empty. It is alive with secrets, each waiting just beyond the edge to be discovered. Beyond the heliopause, Voyager 1 sails through a domain no human-made object has ever explored firsthand. Each fraction of a second that it moves farther from Earth, it gathers new data from a realm once thought to be devoid of activity, yet now slowly, revealing itself as layered, energetic, and intricate. What lies ahead is not an infinite vacuum, but a zone shaped by eons of galactic evolution, a place where ancient stellar events, magnetic interactions, and subatomic forces intertwine in ways we're only beginning to comprehend. One of the more intriguing facets of Voyager 1's ongoing journey is its unintentional role in probing the galactic neighborhood's chemical composition. As it measures particle density and records energetic events, it also occasionally picks up traces of elements and ions that hint at the interstellar medium's material makeup. Although its sensors were not designed to carry out a full chemical survey, the data it sends back helps researchers infer the relative abundance of elements like hydrogen, helium, and heavier ions like oxygen and iron. These findings, limited though they are, point to a medium rich in material ejected from stars that lived and died billions of years ago. Thus, the very space Voyager 1 travels could be seen as the ashes of previous stellar generations, matter that may someday condense again to form new stars and planets. Equally captivating is how Voyager 1 provides insights into behavior of dust in the interstellar medium. Cosmic dust, often overlooked in the grandeur of astrophysics, plays a crucial role in the formation of stars, planets, and even organic molecules. Dust interacts with electromagnetic fields, absorbs and remits starlight, and carries elements crucial for life. As Voyager 1 drifts farther into interstellar space, it occasionally registers tiny impacts from these grains, microscopic collisions that, while seemingly insignificant, provide key data on the density, speed, and orientation of the dust clouds it traverses. These dust grains vary in size, composition, and trajectory, offering clues to their origin. Some may be remnants of nearby supernova explosions, while others could have traveled from distant corners of the galaxy, shaped by the gravity of unseen objects or bent by galactic magnetic fields. The spacecraft long-term operation has also opened up unique opportunities for studying the long-term exposure of materials to space conditions far beyond Earth's orbit. Voyager 1's components, exposed to extreme cold, radiation, and the mechanical stresses of constant motion for nearly 5 decades, offer a one-of-a-kind case study in space durability. The fact that it still operates, even with reduced functionality, gives engineers insights into the kinds of wear and degradation that future spacecraft materials may endure in deep space. This real-world experiment in resilience could inform the construction of next-generation interstellar probes, or even robotic explorers meant to operate in the atmospheres or surfaces of exoplanets, where environmental extremes may be similarly unforgiving. Another compelling aspect of Voyager 1's journey is the way its path intersects with larger galactic forces. The spacecraft is not simply drifting on a linear trajectory. Its motion is subtly influenced by the gravitational pull of the Milky Way, as well as the large-scale currents and fields present in the interstellar medium. These include galactic tides caused by the Milky Way's rotation, the influence of nearby stellar systems, and interactions with the broader magnetic web that threads the galaxy. Voyager 1's data helps map these interactions in a way that was previously only theoretical. As the spacecraft moves, its velocity and orientation offer indirect hints about the mass distribution and force dynamics that govern our corner of the galaxy. By precisely tracking its movement over time, scientists can test hypotheses about dark matter concentrations or gravitational anomalies that remain invisible through telescopic observation alone. Voyager 1 is also offering insights into how solar and galactic processes influence one another across vast distances. Though it has passed beyond the direct influence of the solar wind, the spacecraft still registers echoes of solar activity, particularly in the form of solar shock waves. These energetic bursts, ejected during massive solar flares or coronal mass ejections, propagate to the solar system and continue to travel outward at supersonic speeds. Occasionally, Voyager 1 detects these disturbances, though in a weakened form, suggesting they still have enough energy to influence the interstellar environment. This provides an unprecedented chance to study how solar events evolve as they move away from the sun and interact with different regions of space. It's a slow, stretched-out version of space weather, one that takes months or years to reach Voyager's instruments. Such observations are valuable not just for understanding the sun, but also for building a comparative framework with other stars. If our star's influence can be detected billions of kilometers beyond the solar system, then it stands to reason that other stars exert similar extended influence over their surroundings. Voyager, the first of many, may eventually help define the true boundaries of a star's dominion, not just where its light fades or its planet's orbit, but how far its energetic reach truly extends into the galactic environment. Another profound contribution from Voyager 1 is its function as a reference point in space. Because of its fixed and well-known position far outside the inner solar system, the spacecraft serves as a kind of cosmic anchor. Astronomers use its data to refine models of celestial mechanics, calibrate instruments, and confirm readings from Earth-based observatories. It acts as an outpost for cross-referencing space phenomena. For instance, if a cosmic ray burst is detected by Earth-based instruments and also picked up by Voyager 1, albeit with a time delay, the comparison allows scientists to map the spread and decay of such events across immense distances. In this sense, Voyager becomes not just a scientific instrument, but a distributed node in a larger observational network that spans the solar system. As Voyager 1 continues to provide real-time information about this distant region, it also deepens our understanding of time in a cosmic context. The phenomena it encounters, shocks from ancient supernovae, magnetic structures formed millions of years ago, or radiation fields shaped by epochs of stellar evolution, are relics of a distant past. Voyager 1 is not just observing space. It is observing time itself, moving through an environment that has preserved imprints of events long forgotten by any civilization. In a way, it's like a time traveler sifting through galactic fossils, picking up faint signals from epochs we will never witness but can still interpret through the echo they left behind. It also highlights a seldom discussed dimension of space exploration, the aesthetics and beauty of data from the edge. The signals Voyager sends back are not visible to the human eye, but when translated into sound, light, or visual simulations, they reveal patterns and pulses with an almost haunting elegance. Plasma waves, when converted into audio signals, create eerie whistles and hums that sound otherworldly, an alien song drifting in from the galactic shore. These sonifications serve more than artistic purposes. They offer scientists another layer of analysis, allowing anomalies and patterns to be perceived in ways graphs and numbers can't always convey. If you like this video, please give a like and subscribe to our channel. Also, leave your comments below and tell us what your thoughts on Voyager 1's discovery. What do you think happened? We want to hear from you. Thank you for watching, and see you next time.